Okay, and the last thing that we're going to do after we have finished our layout and it has passed the RC and LBS is to do some parasitic extraction, and that will basically extract resistors, capacitors, sometimes inductors, and then we need to do the simulation to see the effects of these parasitics in the performance of the circuit. So we're going to take here the PBS, and then we need to do some preparation for this. So we are going to run LBS again, but this time in the output we have to enable this create Quantus input data. Quantus is the tool that will generate the parasitic extraction. So we're going to submit, yes. Then let's wait the tool to finish. Okay, it match and it is okay. Can close this, so we close this, and now we go to Quantus, and then we run PBS Quantus. So everything has been predefined for us, including the database that was just been generated by LBS. Click it, and then we need to do some very small configuration here. What we're going to do now is we let everything as it is in the original settings. We go to extraction, and then we are going to change the reference node to ground analog, so this will be the substrate, the node that is connected to the substrate. The other thing is that the capacitor coupling mode, it can be the coupled or the coupled to substrate. I suggest you to keep it coupled. Coupled means that the tool will extract all parasitic capacitance against every single net. So the other two versions are just some simplification of the parasitic extraction, that it will get capacitances to the ground. Yeah, but most of the time you will be worried about the parasitic capacitance between nets, because they will introduce crosstalk. So I suggest you to keep this uncoupled. There are different extraction types for low frequency circuits. Typically you run RC. Sometimes you are interested only in voltage drops, maybe R it is enough for you, and sometimes are you interested in the capacitances, the effect of the parasitic capacitances, then you can use C, but typically you will be running RC. Yeah, the radio frequencies you are pretty much worried about the inductances, and then you will be running RLC or a little bit more complicated parasitic extraction. Then in filtering, you can change the minimum values of the capacitors and resistors that will be extracted, and you can play with this mainly when you have larger layouts, and then it will generate thousands of components. But for now we are going to leave it exactly as it is. So mainly what we are interested in is to change the reference node here. Just click apply, and I will extract, and then it will take a little time before we get the parasitic extracted view generated. Okay, so we have it done. So we can close this, we can close this, and we can even close our layout, and then we can take a look. So there is a new view that is called analog extracted that has been generated, and we can take a look here. It has our layout, or most of our layout here. But what it is interested in is that it also includes some capacitance that has been extracted and also resistances. So let's see what happens when we run the simulation with these components. We can go to our test bench, and to make use for the parasitic extraction, we need to create a config view. So I'm going to delete the one that I already have here to show you how to create one. So let's delete this one. Okay. So a test bench that we use at the beginning, it is here. It has a schematic and ADXL simulation setup. So we're going to go to File, New, Cell View, and then we select here Config. That is the config view. And then we click OK, and then we need to do some configuration. We're going to select the schematic view, and then we're going to use a template. Which template? We use AMS. Okay, okay, and that's it. Okay, we just save this, just close. We can even close this, we don't need it anymore. This also. And then we have a config view. Now we are going to open our design from the config view. So we double click config, and it will ask me if I want to open the schematic also, and yes, I want to open everything. And then we have this very interesting form menu, form field, this window, in which will allow me to select which view from the pump I want to select. I can right click here, and then I can select if I want to use the schematic representation or the analog extracted. So let's keep the schematic for a second. We're going to launch the ADXL setup that we already prepared before with our simulation setups. I need to do something else here. This setup might have been almost always prepared for the schematic. Now it has to point out to this view in which I can switch the representations for the pump, and that is done here for the test in the design. I click it here, design, and then here I can select schematic or config. So I have to make sure that it is pointed to config, because now when I put it to config, it is going to take the configuration that it is here. Now it is selected schematic. I click update here. So I'm going to run the simulation with the schematic. So that was the original simulation of this circuit. And then let's take a look to the netlist. So you see that we are simulating basically the transistors and there is one capacitor and one resistor here. Okay, so it's the schematic level. I'm going to plot it here. So we have it plotted here. And now I'm going to append the simulation results, but now I'm going to select here the analog extracted. I select it. I click the recompute hierarchy. Okay. And now when I click simulation, it is going to simulate the extracted view, which is a simulation that will take a little bit more time because it has many more components. So let's say Okay, now it is finished. I'm going to append the simulation results. So we append, and then let's take a look. I don't need to see the input here. We're going to do logarithmic scale, and then we can see that there has been a variation in the frequency domain here from the schematic to the parasitic extraction. I'm going to do the same here. Zoom in, and yeah, we can see here also that the step response of the amplifier has changed from the parasitic extraction and the schematic. So we can do the comparison and then an estimation if it's still acceptable, the result, and if it is acceptable, the result, we don't need to do any change in the layout. So this is from a performance point of view. We still have to run an emir to check that electron migration and issues are not arising, and IR drops are not arising in our circuit. That will be in a different video. Okay, now the very last thing to do is that we have our op-amp here, and very often we have holes in the layout that are not filled, and what we can do here, it is just to add some extra capacitors to ground, to do some decoupling capacitors filtering the power supply, or some critical net, for instance the biasing, the current biasing. So I'm not going to do that in this design right now, but I'm going to show you in another similar op-amp that I just routed before starting this lecture. So I added component MOS varactor capacitor to the power supply and to the input bias here. So this is going to do a low pass filtering of these signals. And this should be here. I managed to damage my own layout, but let's see. The capacitor was added here. The other capacitor was added here, and then yeah, after I pass LBS, I have to pass LBS again and run the parasitic extraction and run again simulation. Then I can sign off the stage. Now, if for some reason I have to come back and do the layout again, I can remove these capacitors or reduce the sizes if I need to stretch something. So it is always useful to have some space available in case I have to do some changes. Okay, so that will be